Simply supported beams generally have forces acting from the top, which are called loads, pressing it down, and these are the yellow forces F1, F2, and F3, and forces acting from beneath to counterbalance the loads. These are called support reactions. Now there are three conditions for static equilibrium. That means the beam is not moving. The up forces must balance the down forces, so the loads must counterbalance the support reactions. Any force towards the left must counterbalance force towards the right, and all the anti-clockwise movements, the sum must be equal to the sum of the clockwise movements. So the sum of all the moments together must be equal to 0. That way there's no movement. Now this is an example. As you can see, we're taking moments about point A. Point A is the point above support reaction A, and we're doing the forces multiplied by the distance. So these are what you can see in brackets. So F1 times 1 because that is the distance from point A, RA times 6 because that's the distance from point A, F2 times 8 because that's the distance from point A, and then F3 times 11, and all that must be equal to 0 according to the third condition of static equilibrium, which says all the moments must be equal to 0. So any clockwise moment, any moment that is making it go clockwise will be a positive moment. Any moment that will make it go anti-clockwise will be a negative moment. So if you pivot it at A, if you imagine this to be a long ruler with a pivot at A, and then you're pushing it down in the direction of these forces, then if it's going to go clockwise, it's a positive moment, and if it's going to go anti-clockwise, it's going to be a negative moment, and that's what we're doing. Now we're adding all the moments up together, and they must be equal to 0, and at this point we just have an equation, and we're going to find RB from that equation. So we'll rearrange it, as you can see, and then we're going to find the value of RB from the equation. So it's simple mathematics from this point onward. So RB is 37.5. Now we're going to take moments from point B. We're moving the pivot point to point B, no longer point A. And all the distances will be measured from point B. So now it's F1 times 7. And that is negative because if the pivot is at point B and you push down from F1, it's going to make it go anti-clockwise. So that's why it's negative. RA times 6 because that's the distance of RA from point B. And if you push up from RA, it's going to make it go clockwise, and so on and so forth. RB times 0 because the pivot is right on top of RB and it's not going to go anywhere. F2 times 2, which because the distance is 2, and F3 times F3 times 5 because the distance is 5, and all that must be equal to 0 according to the third condition of static equilibrium. So at this point we're going to open the brackets up, tidy up the calculations, and have our equation as we had it before, and then solve that equation for to find RA. So as you can see, minus 45 plus 6RA is equal to 0. So we'll rearrange that. We'll take the negative 45 to the other side, and that will become a positive 45. So 6RA is equal to 45. Therefore, RA is going to be equal to 45 divided by 6. And that will give us 7.5. Now we're going to use the force law, which says the up forces, the forces pushing it up, the RA plus RB, must equal to the forces pushing it down. So if we add F1, F2, and F3, whatever total we get must be equal to the total of RA plus RB. This is the way we know we're right. We can check ourselves and know if the answer is right. So RA plus RB is going to be equal to 37.5 plus 7.5, and if we add that together, we are going to get a total of about 45 newtons. Now if we do the down forces, F1 plus F2 plus F3, we have 20 plus 10 plus 15. So 20 plus 10, 30 plus 15, we still have 45. So that way we know we are right. So please always check your work before you submit it so that you are sure it's right. Now this is another example. It has a different kind of force, and you have your concentrated forces F1 and F2, in yellow, but you also have a force in red, which is called the uniformly distributed load. It's not acting at a single point, it's spread across a distance. Now the secret to solving this type of problem is to convert your UDL to a concentrated load by multiplying it by the distance. So if you take 2.5 multiplied by 4, that will be the value of the equivalent concentrated load, and you put it in the middle of its range. Now we're going to take this as an example. You're going to see how we're going to do this, and what you will find is that clockwise moments are still positive, anti-clockwise moments are negative. The UDL, we're going to multiply by its distance, which is 10, and then we're going to plant it as a concentrated force in the middle of that 10. So we're going to split that 10 into 5 and 5. Now we've started taking moments from about point A, and we're saying force times distance from point A. So F1 times 3 because that's the distance. We have RA times 0 because RA is right on the pivot, so the distance is going to be 0. Now see how we're going to do the UDL at this point. So the UDL is going to be, we take the UDL and we'll multiply it by the distance, which is 10, and then we're going to multiply that by 5 because 5 is the distance from point A. When we convert that UDL to a concentrated load, that concentrated load is going to be in the middle of that 10, which is going to be 5 meters from point A. In this example, it's not always 5 from point A, but in this example, it's going to be 5. And then F2 times 14, because that's the distance from point A, and that's going to be a clockwise moment. Any moment with a positive is going to be clockwise, and any moment with a negative is going to be anti-clockwise. And you can tell that by putting your finger as a pivot and then imagine as a ruler and push it down in the direction of that force. If it's going to go clockwise, it's a positive, and if it's going to go anti-clockwise, it's a negative. Tidying up all these brackets, substituting F1 is 3. We have 3 times 3. RA times 0 is going to be 0. Our UDL is 1.8, so it's 1.8 times 10 times 5, and then it's 8. It's going to be 8 newtons times 14 because that's the distance, and RB times 19 because 19 meters from point A. Remember, it's negative RB because that will make it go anti-clockwise. If we tidy all these numbers up, we put this in, we use our mental math, or put in a calculator, we add up all the numbers and you will get a total take away negative RB. So that's going to be 193, the sum of all those numbers, minus 19 RB, and that is going to be 193 divided by 19 give us RB. RB is going to be 10.159 newtons. Now we're going to take moments from about point B. So we're moving the pivot point to point B, which is over the second reaction force, and we're going to take our distances from point B now. So it's going to be 3 newtons. F1 is 3 newtons times 22 because that is the distance to point B, and it's going to make it go anti-clockwise. If the pivot is at point B and you push it down with F1, it's going to make it go anti-clockwise. RA is at a distance of 19 from point B, but RA will make it go clockwise because it's going to push it up and around, making it go clockwise. Our UDL again, we're going to take the UDL and we're going to multiply the UDL by the distance under the UDL that the UDL is acting on, which is 10, and then we're now going to multiply by the distance of that center point of the UDL to point B. So as you can see, if we split the UDL distance into two, we have 5 on either side, and then we have add that 5 to the distance to point B. The other distances all the way up to point B, and then we're going to have 14. F2 as well will multiply by its distance of 5, and that's going to make it go anti-clockwise. If you add up all the numbers, we open the bracket and then we tidy it up, and then add up all the numbers, and we're going to have 66 minus 66 minus 252 minus 40 plus 19 RA is equal to 0, and that will give us minus 358 plus 19 RA is equal to 0. At this point, it's no longer mechanical principles, it is just maths. So we are just doing our equations, a linear equation, and we're moving move the number to the other side to make it positive, and we now make RA the subject of that equation. RA is 18.842 newtons, which you can find on your calculator by dividing 358 by 19. Now once again we're doing our check. So all the forces pushing down, F1 plus the converted UDL, the UDL times the distance, plus F2, that'll be 3. The UDL times 10 is going to be 18, and the F2 is 8. If we add those together, we get 29. Similarly, if we now look at all the forces pushing it up, RA plus RB, RA is 18.842 and RB is 10.159. If you add those two numbers up together, you get 29.001. They're very, very close. That is enough. That's a good check.